it's 8 o'clock. Oh, a little bit late this morning. Oh, goodness. All right. Let's see. Well, you have homework due this weekend, but we are almost finished. I'm going to talk about some applications of integration today, but I'm not going to cover it in any depth. We've done, and certainly by Monday, I will be done talking about all the new material. So we'll spend next Tuesday and Wednesday reviewing. Yeah, you will have one more homework assignment. I'll get it up this weekend, but it'll be a short one for once, okay? Any questions?
Hey, Ms. Kennedy, how are we going to be doing our final?
I was thinking just same way we did our exams, okay? So we'll just, well, it's set at a certain time, and I'll use that time, and I have to see everybody on camera. Somebody always has internet problems, so I'll use, there are actually 2 exam slots I could use because we are Monday, Wednesday, and Friday. We are also a Tuesday, Thursday class. I'll use the second exam slot for anybody who couldn't take the original, and I'll give them a final on campus, but that won't be very many people, okay? And it'll be another exam too.
Oh, all right.
Yeah, so it'll be the same way.
Okay, thank you.
You're welcome. And I have to look at the syllabus. The date is on the syllabus. We'll talk more about that next week. Also, over Thanksgiving, I'm going to get all your grades together. And I'll send each of you an email with your exam grades and your homework grades so that you can check them for one thing. But that way you will know exactly what you have going into the final. Okay? All right.
Just to let you know, my parents are installing a antenna that's supposed to boost my internet.
Well, good.
Now, so if my computer starts acting funky, that's why.
Okay. Yeah, internet, we always have, everybody has internet problems from time to time, and I've tried to work on mine. I guess it's been so important the last 9 months in particular to have internet. One would hope that there would be efforts in this country to make sure that everybody has access to good internet. I would have been up a creek if I hadn't had it. It's been hard enough these last 9 months, and without internet, I don't know, I would be totally isolated. But I can still see everybody over Zoom and FaceTime. Okay. All right. So very last thing we're going to do. Let's see. Okay. No, I want to get rid of that. Get rid of that. Okay. Is some applications of integration. Well, let's see. So okay. If you make it all the way to 3rd semester calculus, at the very end, and certainly if you're in engineering or taking calculus-based physics, integrals are really foundation of Maxwell's equations for one thing. Okay, but there are lots of other applications for computing work and force and flow. Oh yeah, a whole bunch of things. But we're going to do just a couple of simple ones. Basically, the idea is if you can approximate quantity with Riemann sums, then you can compute it with an integral. A definite integral. And by approximate, I mean you can get as good an approximation as you wish. So let me show you what that means. Let's start with, okay, and maybe I need some grid. Some area problems. Okay, and actually, I'm going to cover this lightly. We could spend a lot of time talking about it and make some rules, but I just want to think about it, think about what the Riemann sum approximation would look like, and from there get the appropriate integral. Okay, so suppose we have this problem. Find the area of the region in the plane. I should say that. That's bounded above by the curve y equal to e to the x, and bounded below by y equal to x, and bounded on the sides by x equal to 0 and x equal to 1. Okay. Well, first thing I do, draw a picture. So, okay, let's see, y equal to x. I don't need negative values. Okay, x equal to 0. Let's see, I'm going to call that 1. So when x is 0, so that's going to be my right boundary, but let's get the curves first. Y at 0 is 1. That's e to the 0. Oh, okay. I'm getting my curves. Okay, and right now I'm sketching y equal to e to the x. And at 1, it's e, so I'll just call that e up there. And it's goes from one point to the other, increasing. And let's see. Okay, oops, I went further. Okay, I guess that's 1. Somebody entered. Don't know why he's coming now. Okay, let's see. There. Okay. Y equal to X. Okay, well, that's one. That's just the diagonal line. Okay, and then X equal to 0 is that piece of the Y axis, and X equal to 1 is that vertical line. Okay, so that's our region, and we want to find the area. Of all this stuff. Okay, this region. And that's not a rectangle or anything that I have a formula for the area of. What do I know? If I want to approximate this with rectangles, okay, they would, divide this up into a partition, the interval from 0 to 1, and then let's use right endpoints to get the height. My rectangles, okay. I could think about my rectangles going from the top curve to the bottom curve. And I'm using right endpoints to get those. Draw all that. Okay, looks like that. And one last one. Okay, so it looks like, how many things do I have in my partition? 1, 2, 3, 4, 5, 6. N's equal to 6. So I've got 6 rectangles that go from the top of the curve to the bottom of the curve, and they all have width. B minus A over 6 would be 1 minus 0 over 6. So my Riemann sum, the area of the rectangles, well, the first rectangle would have area F of x1 minus G of x1 times delta x. Okay, because it goes from the height goes from the bottom curve to the upper curve. That's true for each rectangle. Where, okay, f of x is the top curve and g of x is the bottom curve. Okay. And the next rectangle, it would have area f of x2 minus g of x2 times delta x, and so forth, all the way to number 6. So my Riemann sum is going to be the sum as I goes from 1 to 6 of f of x sub I minus g of x sub I delta x. Okay, well, that was for n equal to 6. But I could go back and I could, divide these intervals in half and get a better approximation, right? I can get as good an approximation as I wish. So that means that for this problem in general, for any given n. I'll have a Riemann sum that looks like I goes from 1 to n, and then f of x sub I minus g of x sub I delta x. And I have too many parentheses. Okay. All right, which in this case, the top curve was e to the x. The bottom curve was y equal to x. So it'd be that. Those are Riemann sums. So if I take the limit as n goes to infinity of my Riemann sums, this is why an integral will do the job for us. Oops. Okay, delta x. Well, that is the definite integral from 0 to 1 of e to the x minus x dx. Did somebody try to enter? No, apparently not. Nope, okay. Okay. And that is going to give me the area. Exactly. Okay. So it's just a matter of working out the integral. So let's see. Any derivative of e to the x is e to the x. Any derivative of x, x squared over 2. I want to evaluate from 0 to 1. And that's going to be equal to e to the 1 minus 1/2 minus e to the 0 minus 0, which is, okay, e to the 0 is 1. So e minus 3/2. And, okay, that is a positive number. Okay, if you're computing an area, you should get a positive number. And e is about 2.718, so that's going to be positive. Okay, so we're going to move from a Riemann sum to a definite integral. Any questions? Are you all still there?
Yes, ma'am.
Okay, good. That seems pretty straightforward, right? But you could also think of this, well, you get the area under e to the x, you get the area under g, or which is x, y equals to x. You subtract the top one minus the bottom, that would do the job too. But this idea of thinking about the Riemann sum of, the rectangles that would do the approximating is a really useful one. Okay, let's do another one. Speak up if you have a question. Okay, this is also an area problem. Okay. Find the area enclosed by okay. It should be the area of the region. Yeah. If you're a mathematician, you like to use words carefully. It's really important to say exactly what you mean. Enclosed by the line
y equal to x minus 1. And the parabola y squared is equal to 2x plus 6. Okay, so we got to figure out what the region is first. All right, so draw a picture. And this one, okay, let's see if I can. Here's my coordinate system. Y equal to x minus 1. Call that minus 1. Okay, so that's a straight line. Don't really know how much of it I need to draw. So that's, yeah. For a line, it's a line, so you only need 2 points, right? So I didn't plot any points. But I know that at 0, y is minus 1, and at x equal to 1, y is 0. That's my 2 points right there. But let's see. Let's plot some points for y squared equal to 2x plus 6. And, well, that's a parabola on its side. I can, okay, all right. Y squared minus 6 is 2x. Y squared minus 6 over 2 is x. It's easy to write that as a function of y. If I do keep it in this y as a function of x, well, y squared equal to 2x plus y. That does not give me y as a function of x. Explicitly, it's implicitly defined. As a function of x, it's really 2 functions. Okay, but I'm going to use this. Let's see. And I'm also going to need to know where these 2 curves intersect. But let me just plot some points first. So I'm going to go in reverse order here using x is, well, reverse from what we usually do. Okay, so if y is, let's see. Let's start with these points. Y is 0. X would be minus 3. If y is 1, and I get the same for 1 and minus 1, so 2 for 1 here. I get 1 minus 6, so minus 5 over 2. At 2, so that'd be 4. Let's see, yeah, 4 minus 6, that's going to give me minus 1. Minus 1. I think I need some positive values here. Let's see. At 3, I would get 9 minus 6. So plus 3 halves. Okay, so I think maybe the vertex is right there at 0. Okay, now I got to remember it's y. Y is 0. X is minus 3. Okay, that's on that parabola. And let's make the parabola a different color. Okay. So that point's on the parabola. If so that was that point right there. If y is -1, that's there. X is -5/2. So about right there. If y is -2, that's there. Right there. Okay. -2. X is -1. Okay, I think I'm screwing up. I know I am. If y is 0, x is -3. I'm definitely screwing up. Okay. All right. So used to thinking of y is a function of x. Okay. If y is 0, right. Okay. If y is -1, x is -5/2. So that's about there. Ah, there. Okay. And it's also the same for +1. And if y is -2, x is -1. Ah, yes, I'm coming back. Okay. Uh-huh. Okay. There. If y is, how about +2? Oh, I just got that one. Y is 3. X is, what's that? 3/2? Yeah. If y is 3, x is 3/2. Okay, which puts it about there. Okay, so my curve, this is enough. In fact, I got one of the intersection points. It's right there. But I need that one too. Because, yeah, here's my region right here. The parabola keeps going, of course. The line keeps going in the other direction. My region is this. So I need to know what those intersection points are. And to find those, let's see. So set my curves equal. Well, all right. It's easy to solve for x as a function of y. And the other one I can write, okay, y is equal to x -1 means that x is y -1. Oh, +1. Add 1 to both sides. Okay, so that would give me that. And then solve for y. Okay, that would say y squared -6 is 2y plus 2. Y squared -2y -6 minus 2 is 0. And so y squared -2y -8 is 0. And 4 and 2, surely. Okay. Would that be a factorization?
Y squared minus 8 minus 4y plus 2y. Yeah, I think that works. So that says,
Is y plus 1 intended to be the original straight line?
yes. Yes.
Okay, thank you.
Okay, yeah, it was given originally as a function of x, but it's easy to switch it over to a function of y. Okay, and yeah, it's easier. If I think of y in terms of the parabola in terms of x, I have to think about two functions. So I was just thinking. In fact, yeah, we'll do both. Y is a function of x and x is a function of y as far as this Riemann sum in a minute. Okay, but not there yet. So y is 4 or y is minus 2. And I think we already found the minus 2 just because we happen to plot it. But y equal to 4. Okay, so let's put that in our list. Y equal to 4 gives x equal to, 16 minus 6 over 2. 10 over 2 is 5. And, okay, so 4, oops, I have to remember that's backwards. That x, yeah. So 5, 4. 5, 4 is point of intersection. And also this one, minus 1, 2 is the other one. Okay.
Wasn't it minus 1, minus 2 that was the other intersection point?
Yeah. Thank you, Mr. Levy. And that's the kind of thing that would mess everything up too. So thank you very much. Okay. Okay. So let's label those points. This one is minus 1, minus 2. And the other one is 5, 4. So my little sketch here looks a little off, but it'll serve. Okay. So now I'm going to approximate the area of this, right? With rectangles. If I try to do it vertically, okay, so let's take, again, about this way. There's supposed to be symmetry on this parabola about the x-axis, and mine is not exactly symmetric, but okay, if I'm using rectangles here, so I use the right endpoints. Oops, no, not that far. Okay. And this one, this one, this one. That should be just a line. Okay, top to bottom, I would get these rectangles. And I could set up my Riemann sum. But you might notice something here. To the left of the y-axis, the top and the bottom of the region are both determined by the parabola. To the right of the y-axis, the top is the parabola curve and the bottom is the straight line. Well, actually, that's the straight line too, so it's not completely just left and right. So the boundary curves changed. Okay, so if I want to
Yeah, so the approximating rectangles over here go from the top of the parabola to the bottom of the parabola. Approximating rectangles over here go from the top of the parabola to the line. Okay, and that has to be taken into account. So basically, if I want to do this with the vertical rectangles, I got to split up what I'm doing to the stuff that happened before x equal to -1, and then what happens after x equal to -1. I really need two different Riemann sums. Okay, so for, I'll call them vertical rectangles. Actually, it's easier here if we think horizontally. So horizontal rectangles, and we'll do that in a minute, but let's do it with the vertical rectangles first. To the left of x equal to -1, that's when the top is the parabola. In fact, the top is the plus square root. Two x plus 6. And the bottom is also the parabola, but it has curve y equal to minus the square root of 2x plus 6. Okay, so I really need, and then, yeah, this happens to the left, to the right of x equal to -1. The top is the parabola y equal to plus the square root of 2x plus 6. And the bottom is a line. Oh, I need to sneeze. Sorry, I could feel that coming on. Bottom is a line y equal to x minus 1. Okay, and the top of, yeah, when the curves change, your Riemann sum's got to change too. So for the, to the left of x equal to -1, Riemann sum would have the form I goes from 1 to n of, okay, the square root of 2x plus 6, 2x of I plus 6, minus the square root of 2x by plus 6. Well, minus actually, because the bottom is the bottom of the parabola, delta x. Okay. And to the right, the Riemann sum would be, it goes from 1 to n of the square root of 2x sub I plus 6, that's the parabola, minus the line, x minus 1, yes. Okay, so this is going to lead to the integral. It's going to lead to two different integrals. To the left of x equal to -1, it's going to be the integral from, okay, so my x's go from -3, wasn't it? Yes. My x's go from -3 to -1, the square root of 2x plus 6. Minus minus is going to be a plus, the square root of 2x plus 6, dx. Okay. And to the right, it's going to lead to the integral from -1 to, what was that? Was 5? Yes. -1 to 5. That was that other intersection point of the square root of 2x plus 6 minus x. Oh, yes, right up there. Okay, leads to that integral. So the area here is the sum minus x plus 1. Go ahead and do that. Okay. The sum of those two integrals. And let's see, it's 842. Well, we'll work that out either today or on Monday. But right now, I want to show you how to set it up in a simpler way. So let's just draw the whole thing again. And okay, if I think left to right instead of top to bottom, and think about rectangles going this way, then the left curve is the parabola and the right curve is the line, and there's no change in the middle of the interval. Okay, so let's just draw. Draw this picture again. And x minus 1. And the parabola, make the parabola blue, goes from there. 1, 2, 3, 4, 5. 5 was supposed to be 5, 4. And I'll call it that. Okay. So it doesn't exactly match up with my grid there. All right. So this point was 5, 4. Yes. And the other point's -1, -2. And now, okay, I'm going to draw my rectangles horizontally. So, well, let's see, I guess I should start here. Okay, partition first. So I'm partitioning the y-axis instead of the x-axis. And, okay, so the rectangle go from left to right. This one left to right. um, this one left to right, and that's supposed to be okay. And actually, yeah, that would be 0. Okay. My picture's not great. Down here, left to right, and this one, well, that's a point of intersection, so the left is the right. And that would give you a 0 rectangle too. Okay, so we're going to take our rectangles drawn horizontally and think of x as being a function of y. And the Riemann sum then okay, so this curve is, forget, y squared minus 6 over 2. And this curve was y plus 1. And the parabola is always the left boundary. The line is always the right boundary. I only need one integral. And it will go from, oh, wait a minute. I'm doing the Riemann sum first. Okay. Riemann sum will be the sum as I goes from 1 to n of y. Let's see. I guess I should take the right curve and subtract the left curve. So y sub I plus 1 minus, the length of that line would be y sub I plus 1 minus the y sub I squared plus 6 over 2 delta y. And that's going to lead me to the integral from -2 to 4. This is y-axis now, of y plus 1 minus y squared plus 6 over 2 dy. Okay, so that should be the area also. And of course, this integral, which is a number, definite integral is a number, should be the same as this number, which is the sum of 2 definite integrals. Well, let's see if I can compute this one first. Okay. All right, so the area then. Oh, before I go further, are there questions? Are you all still there?
Yes, ma'am.
Okay, that's good. Area is equal to I'm gonna, it's okay, go straight to the antiderivative, which is pretty straightforward here. Y squared over 2 plus y, and that's y squared over 2. So that would be y cubed over 3, and that was plus that, well, minus 3 y. Okay. That goes from -2 to 4. And I may as well combine that and that. Minus 2y minus 1/6 y cubed. And that would be 16 over 2. Stop that. 8 minus 8 minus 1/6 times 4 cubed is 64. minus, now this is an area, so I should come out with a positive number. Okay, that doesn't look, that's not positive. Okay, but I still have more stuff here. Okay, so minus 2 squared is 4 over 2 is 2. And then plus 4. And then plus 1/6 times 8. See, this is not looking positive to me. Oh my God. So I screwed up then. That's a negative number. Okay. Because it's 8 minus 8. And then minus 64 over 6. And that's definitely positive. So that's minus 6 minus 8/6. Did I get the top and the left and the right wrong? No, it should be this minus that. Oh, well, I guess I better figure out what's wrong there. Yeah. Okay. This is wrong. So, which means I screwed up. This can't be right. Areas are positive. Okay. But okay, we're pretty much out of time anyway. I will figure out what is wrong. Maybe, I don't know. I don't know what I did. But I will figure it out and I will fix it on Monday. And we will also work out this pair of integrals. We should get, well, I hope we don't get the same thing as we got here. That is a negative number. Yeah, this cannot possibly be right. Areas are not negative. Okay, so class is over. I'll see you guys Monday. We're getting, 3 days next.
See you on Friday, Miss Kennedy.
Professor Kennedy, are you still there? See you later.